Anyway, there is the Albuquerque Isotopes baseball team mascot, Orbit. We can wonder why they would say a big fat orange thing would be their mascot, but you got to have a smiley face. Looks like a dog, kind of. Everybody likes dogs. But it is interesting to know. One hopes that they're stable and not unstable, but we are talking about minor league baseball. So let's talk about radiogenic isotopes and geochronology. So we were talking about stable isotopes. Now we're talking about unstable isotopes, or at least they're unstable until they get to their final daughter product. So in the case of uranium lead, which we'll talk about a lot, uranium is unstable, it's radioactive, and lead is stable, but we really don't think of lead as a stable isotope. We talk about it as radiogenic, right? Created by radioactivity. So these two applications naturally divide the lecture. Number one, we can use these to determine the radiometric ages of rocks. And this is one of the great gifts that the nuclear bomb gave geology, was the ability to determine the ages of things. And then we can also use it for identifying the sources of the rocks that contain the deposits. So we'll talk about both of these in turn. First, we'll talk about dating. So let's just take a quick watch a video, huh?
This lesson looks at why some isotopes are radioactive. You may wish to refer to the lesson Why Aren't All Atomic Masses Whole Numbers to help you understand this video. The identity and chemical properties of any atom are determined by the numbers of protons in its nucleus. As atoms get bigger and heavier, the nuclei get bigger and heavier, and the protons need a sort of nuclear glue to help hold them together. Neutrons provide this glue and prevent the positive charges of protons from repelling each other, thanks to something called the strong nuclear force. Elements can exist with slightly different numbers of neutrons, and we call these isotopes of an element. It is particularly common for heavier elements where a lot of neutrons are required to hold the nucleus together, but smaller and lighter examples include the isotopes of hydrogen. Hydrogen-1, hydrogen-2, also called deuterium, and hydrogen-3, also known as tritium, are the three isotopes of hydrogen. They have 0, 1, and 2 neutrons respectively. Tritium is the heaviest isotope of hydrogen as it has a larger mass number. Note that in each of these isotopes there is a single proton. This means that the element is unchanged, and that's the important point. It is still hydrogen and will react chemically in exactly the same way. There is often more than one stable isotope of an element. In fact, much of the world around us is made up of stable isotopes. However, sometimes there aren't enough neutrons in a nucleus, or there may be too many for it to be stable. An analogy is a person carrying boxes. If you try to carry too many boxes, you'll end up dropping some. And if you continue, you'll keep dropping boxes until you reach a manageable amount. This is your stable state. And nuclei behave in a similar way, and they will try to stabilize themselves. If there are too many protons or too many neutrons, the nucleus can spontaneously rearrange itself and throw out particles in the process. This is essentially what happens in radioactive decay. Isotopes that have unstable nuclei like this are known as radioactive isotopes or radioisotopes. In our hydrogen examples, tritium are unstable and are hence radioisotopes of hydrogen. The more unstable a nucleus, the faster it will try to rearrange itself into a more stable state. And another name for this process is radioactive decay. Radioisotopes are often used in medicine to trace aspects of body chemistry or blood flow. For example, a small amount of the radioisotope technetium-99 may be injected into the bloodstream to show up on medical imaging and X-rays, and this is known as a medical tracer. Tracers can be used by chemists to understand how a reaction works. Atoms of radioisotopes can act as markers, allowing chemists to follow how a reaction sequence occurs. And of course, radioisotopes are also used in radiotherapy to kill malignant cancer cells. So, as you can see, isotopes are important in modern science, and so we'll finish with a summary of the key points. Isotopes of the same element have the same chemical properties. Some isotopes are stable. Isotopes that are unstable are radioactive. Radioactive isotopes are also known as radioisotopes. Radioisotopes can be used as tracers or markers in chemistry and medicine, and they are also used to kill cancer cells.
Okay. What was that? All right. So we've been talking about unstable nuclei, which is what we're talking about. And so these are all radionuclides, radioisotopes: potassium 40, rubidium 87, lutetium 176, samarium 147, rhenium 187, 232 thorium, 235 uranium, 238 uranium. So these are all radioactive, and we can talk about how unstable they are by looking at their half-lives, right? This is basically the measure of how long it takes X amount of a radioisotope to turn into 1/2 X of that. And there's the half-life in years. That's potassium 40 is 1.25 times 10 to the 9 years. Rubidium 87 is 4.88 times 10 to the 10 years, etc. These are the decay types, the different styles of decay. This is the decay constant, which is related to the half-life. So as it turns out, the shorter the half-life, the higher the decay constant. Right? These are all very small numbers, but 10 to the minus 10 is bigger than 10 to the minus 12. So this has a shorter half-life than this has, right? Quite a bit. And then here we see what these elements turn into. So I'm sorry, isotopes. Potassium 40 turns into either argon 40 or calcium 40. Rubidium 87 turns into strontium 87, et cetera, et cetera. And this shows the relative abundances in nature. Don't have to worry about that. And then this shows the ratios that are being measured by the instrument. So just to summarize, the decay constant is basically the probability of decay. So these decay constants are in units of per year. So that is the probability that a nucleus of that isotope would decay into argon 40 in any 1 year. It is a completely random event, but it occurs with a well-known probability. So one of the things that's worth knowing is that essentially all of a radioactive isotope is gone after 10 half-lives. So this tells you, how far back is carbon-14 useful, right? People think we're dating the dinosaurs with carbon-14, which we can't. But if you think about it, does anybody want to take a shot at this? If the carbon-14 half-life is 5,700 years, how far back in time can we usefully use carbon-14 to date anything? So just raise your little hand. You got to find that little button.
Sorry
to
about that. I
unmute you.
couldn't get my cursor.
There we go.
Stuck in something else.
There we go.
57,000 years.
Yes. I mean, so, Matt mentioned 50 to 60,000 years, but, that's what it comes from. And you can do this, you can see that, look at the half-life for uranium-235. It's 700 million years. So it's like 10 half-lives. Ooh, that would be, if we were 7 billion years, if the Earth was 7 billion years old instead of 4.565, there'd be no uranium-235, and we would have never invented an atomic bomb, because you've got to have that. But unfortunately, we're not, so we got it. So anyway, that's half-lives and decay constant, and I suspect there'll be a midterm question on that. All right, so this sort of shows you how these different elements decay with time. So this is the parent existing over the original parent. So this is the rubidium-strontium scale. So 87 rubidium has got a very low decay constant and a long half-life. So it hasn't changed much over Earth history. But uranium-235, man, we've got just a trivial fraction of that remaining from what was originally present on Earth, and likewise with potassium argon. Okay, that makes sense. All right, so let's talk about how we use this to determine the ages of rocks. So geochronology is the field. This is where we determine we use the radioactive decay of certain elements in certain minerals to determine the age of mineralization and host rock formation. So older rocks have higher ratios of daughter to parent. Younger rocks have lower ratios of daughter to parent, right? There's a very simple relationship between the amount of daughter parent product and the amount of parent, that ratio, and age, that allows us to determine the age incredibly precisely nowadays. All right, so this is the radioactive decay equation. D equals D naught plus P times E lambda T minus 1, where D is the daughter at any time T. D naught, it was the original daughter, and the radioactive parent. Okay, so this is the equation, and we can rearrange this to solve for time. And so the age of anything that follows this relationship is just T is equal to 1 over lambda, the decay constant, times the natural logarithm of D minus D naught divided by P. Okay? All we need in order to get an age is determine the relative proportions of parent and daughter, constrain the original initial daughter so that we know when we know it was there when the radiogenic started accumulating, and know a decay constant, right? You will not be asked to memorize this on the midterm, but that's where all ages come from. And when you get in discussions with people that don't understand geochronology, it's useful to show this to them, because it's really quite simple. The devil's in the details of how do we get these pieces of information. But that equation is all we have to solve. And I'm happy to entertain questions. All right, so let's start off with rubidium-strontium dating. So rubidium is the radioactive parent. 87 strontium is the radiogenic daughter. And we're ratioing them both to 87 strontium, 86 strontium, simply because it's easier to measure ratios than it is to measure absolute amounts in general. So rubidium-87 decays to strontium-87 with a characteristic decay constant half-life. Now, the problem is that there's an awful lot of strontium-87 already around. It was present at the beginning of the Earth. So we have to figure that out. And the way we can do that is to develop what's called an isochron diagram, where we take 4 samples, which they were in isotopic equilibrium at the time they formed, but because they had different ratios of radioactive parent to radiogenic, radioactive parent to this other, the ones that have the highest ratio are going to evolve the most, and the ones that have the lowest ratio are going to evolve the least. But they'll line up on a line, what we call the isochron, which is the same age. And this slope of this line gives you the answer to your age, because it's just the slope is equal to e to the lambda t minus 1, right? If you look at this equation, that's just a very simple equation of the form y equals mx, that's mx plus b, right? So m is the slope of the line, so that is the slope of the line. All right. So all you do is you analyze 4 things. These could be 4 minerals from the same body, or 4 rocks from the same body, or whatever. And calculate the slope of the line, see how good the data fit. So this is a question for somebody in the class. What is older, something with a steeper slope or something with a flatter slope? So somebody want to answer that question? Don't be shy. Oh, you want me to call on you? Fair enough. Katie, which one is older? The one with a flatter slope or the one with a steeper slope? You're gonna have to unmute. Can you unmute? And if you don't know, just talk to us. That's fine. Are you unmuted yet?
Yeah,
Yeah,
I'm muted.
go ahead.
I guess something with a flatter slope is older.
No, it's something with a steeper slope, because in order to go from here to here takes time, and to go from here to here takes more time, and so on like that. So the flatter the slope, the younger the age. The steeper the slope, the older the age. But yeah, you have to sort of reason those things out. Does everybody see that? Okay, good. So that's me many years ago analyzing a sample for 87 strontium, 86 strontium on the UTD Geosciences mass spectrometer. That would have been in the late 1980s. And this is a HP 87 computer, very modern at the time. And this is the sample. You can see it glowing in there. This is all in a vacuum, and those are the vacuums. And then you just heat it up, and then that evaporates it and ionizes it, and it's accelerated through a magnet. You can sort of barely just see the magnet back here, and then collected up here on top. But yeah, that got me tenure. All right, so in fact, we're using rubidium strontium technique to determine ages of ore deposits. So this is rubidium strontium isochrons for pyrite, some subsamples from a gold mine in China. IR is this initial ratio we talked about, right? It's basically where the 87-86 ratio, 87 rubidium 86 ratio goes to 0, which must have been the original ratio. If this value is 0, then that hasn't evolved at all. So here is one vein with 4 pyrite samples, got an age of 122 plus or minus 11 million years with the initial ratio of that. And this is a statistical measure of how good the data fit the line, right? You can have data that fit the line perfectly, in which case the MSWD is very, very low, maybe 0, or it can not fit it very well, in which case the MSWD is high. And in this one, it seems pretty high. MSWD at 25 is pretty high. So it's like a purist would say, well, that's not a very good age. Okay. So here's another one. This is a different vein from a different ore deposit. And these 5 points define but basically the same age, but with a better MSWD and initial, right? So this pyrite mineralization seems to have occurred about 123 million years ago. And there's a third one with an even lower MSWD. So this all makes sense because these bodies are all associated with early Cretaceous igneous rocks, probably in northeast China. I'm not sure where exactly it is. And in addition, you get this information from the initial ratio that suggests that the involvement of continental crust is in there, and that is also useful too. We'll talk more about that later. But you can see how you can get ages on ore deposits using these techniques. Now, the amazing thing is how little. Okay, here's another example. This one is a complex relationship of in a outcrop. There's the gold lode in white. Then there's the alteration zone around it. Then there's a feldspar porphyry dike that comes across it. Basically must be younger than the ore mineralization. And then there's the granite that's sort of hosting it. And then there's the mafic dike that's sort of paralleling it. So you would think that the granite, because it's being intruded by the mineralized zone, is the oldest, and that this cross-cutting feldspar porphyry dike should be the youngest. And let's see, the granite is based on uranium lead age is 126 to 130 million years. Okay. That seems like the oldest age in here. The plagioclase porphyry dike has got an age of 120. So that constrains this mineralization from that argument alone to be on the order of between 120 and 130 million years. So then we can take the rubidium strontium ages of the pyrite and get an age of 122 to 123 million years. That fits. And the mafic dike, which seems to have come in around the same time, that also fits. Now, the alteration zone, you don't get as tight of a story, but alteration zones, those are easy to disturb. But the nice thing about this diagram is it shows you some of the complexity that it needs to be worked out at any ore deposit. It's never going to be as simple as we might want, but you'll get these relationships, and you can almost imagine the scientist or the team looking at the outcrop going, now, how can we attack that with the tools that we have? And that's a good example of how to do that. Yeah. Now, another approach, we were talking about rubidium strontium. Let's talk about potassium argon and argon dating. So this requires a slight diversion, the reasons of which will become apparent shortly. But basically what neutron activation is you take your sample and you put it in a nuclear reactor where it's bombarded by neutrons from the nuclear reactions going on, and that turns it into a brand new mineral element. So used to be the way we got trace elements, but now the best way to get trace elements is by ICP-MS. But what we can do with this, where it's still useful, is to make potassium argon dating better. So what you can do, the actual decay scheme for potassium to argon is potassium 40 to argon 40. Now, there's not much potassium 40, but there's a lot of potassium 39. And we know the ratio of potassium 40 to 39. So if we determine how much potassium 39 is in there, we can figure out easily how much potassium 40 is in there, which is part of what we need to know in order to calculate an age. So what we do is we turn this into, we turn the potassium 39 into argon 39 by bombarding it with neutrons in a nuclear power plant. And then we can analyze the argon 39 and the argon 40 together to get the age. Now, here we've got the potassium argon scheme, right? So what kinds of rocks are best for potassium argon dating? Does anybody want to take a guess? It's, obviously potassium rich rocks. And rocks that don't have
Or
the
the
other
old
things.
ones.
Well, the old ones, yeah. The older the rock is, the more of the daughter product you have. But argon is a gas, and so it will escape. But Andrew, you got a answer?
Yeah, is it something with like a lot of feldspar in it, like a lot of K-spar in it, like a granite?
Yeah, or biotite, so rocks that contain a lot of potassium-bearing minerals are very good. Now, the other thing that potassium argon and its close relative argon-argon dating is used for now is volcanic rocks. These are very difficult to date any other way because they don't, often they don't, especially basalts, they don't have any zircon in them. But yeah, so biotite, hornblende, those things contain potassium, and the rocks that contain them are good. So you have to be sensitive to what your scheme is, and then think about, okay, what minerals in my rock are likely to have those elements, if any. All right, so basically the principles of potassium argon dating is, you've got a molten lava, and when it erupts, it releases all of the argon to the atmosphere. So the only thing that's in the lava is potassium 40. After it cools, right? Now, slowly as it's cooled, the argon is potassium 40 decays to argon 40, and in an old lava that you'll get something like that. Now, the problem is it requires two measurements, separate measurements. One of them is determine the concentration of potassium in your sample. Could be a rock, could be a mineral. And the other is to determine the concentration of argon and the abundance of argon 40 in your sample. And one of them requires a different analysis than the other, and that introduces error. But if with the argon, with neutron activation, we can turn the potassium into argon, then we have another tool. And what's cool about this is potassium 40, argon 40 dating with a twist. So basically, this is the argon, this is what's called a release spectra for argon 4039. The 39 is there because potassium 39 is turned into argon 39 by neutron activation, and then we can calculate how much potassium must be in there from that relationship. So what happens is after radiating your sample, you take it to a mass spectrometer, release the gas, and measure it. Now, what's cool is you can do this in a way that allows you to figure out whether or not you've got a complex situation, because mineral deposits have it's often complicated. So you can do what's called a step heating spectra. So basically, what you do is you heat up the sample and to a few hundred degrees, and so it releases, what's that, about 8% of the gas, and then you turn it up another 50 degrees and it releases another 12%, and then you heat it up again to a higher temperature and it releases 40%, and then again 60, and then again until it's all gone, until you have 100% of the gas, the argon 39 is released. And if you have what's called a well-behaved sample, you'll get what's called a plateau age, where the age of each of these segments is essentially the same. And you can report what's called a plateau age. This is for a sanidine crystal in rhyolite, and it's 1186.7 thousand years, so about 1.2 million years ago. Okay. Any questions about that argon step heating? It has made it possible not only to get ages, but also to evaluate things like where is the argon being held. Now, it also lets you go, okay, we don't understand what's going on. So here's, argon 4039 step heating spectra for a muscovite, a mica from a gold deposit in the Klamath of California. And what you can see here, is this Yankee John deposit. There's two spectra in here. That looks like three spectra in here. That, 153 plus or minus 19, 152.1 plus or minus 1.7. And then I can't really see this other one here, I guess. But you can say, okay, that's pretty well behaved spectra. And so it inspires confidence. Okay, we know that this system hasn't been disturbed. But then we look at another one like this, where you get a bunch of ages, out to a small amount of the gas being released, and then you get a different age. When you release more, you're going, I'm not sure what's going on, and you have much less confidence in that age. And that's the ability to look at these release spectra and determine whether or not the system is well behaved is one of the very nice things you get from the argon 4039 step heating method. Any questions about that? All right. Now, geochronology in a lot of cases is focused on uranium lead dating, and in particular in zircons. It's really the queen of geochronology in many ways, because it can be used to date rocks that range in age from about 1 million years to over 4.5 billion years, with routine precisions and very low. So this is sort of a nice crystal of zircon, ZrSiO4. Very hard, tough mineral. And what you see is that zircon plus 4 has an ionic radius of 86 picometers, whereas uranium plus 4 is 103 picometers. So that's close enough to zircon to substitute. That's with like the 15%, put right at the edge of 15%, Goldschmidt's rules. And the ionic charge is the same. So uranium substitutes pretty well in the zircon lattice, but lead doesn't. Lead is excluded. All right, let's watch a video.
So here's the question: is what for the progressive creationists, what is it that they have chosen to believe is true about history that now requires them to want to look at the text differently than those who are on, we would say, the young Earth position?
It's interesting. Again, I like to look at it historically. So the real issue are the rocks.
When it comes to the age of the Earth, there are two schools of thought: the young Earth model and the old Earth model. Even today, people are still debating whether the Earth is young or old. Even though back in the 19th century, scientists were already beginning to question the legitimacy of the young Earth model. Scientists didn't have a reliable mechanism for dating the age of rocks until the 20th century, with the advent of radiometric dating. By measuring the ratio of radioactive isotopes, we can now calculate the age of rocks on a large scale. So how old is the Earth? Let's look at 4 key pieces of evidence that support the theory that our planet is over 4.5 billion years old. To find Earth's oldest rocks, we will need to look at Archean cratons. These are massive remains of early crust produced by Earth. The oldest rocks found within these cratons are in the Acasta Gneiss complex of Canada. By measuring the ratios of uranium, geologists have dated these rocks to an age of 4.03 billion years. The oldest minerals on Earth are zircon crystals found deposited in younger rocks in the Jack Hills Formation in Western Australia. Even though the surrounding rock is much younger, these zircons crystallized a long time ago and were recycled by Earth's natural rock cycle. By measuring the ratio of lead isotopes in the zircons, scientists have dated these at 4.4 billion, even older than the Acasta Gneiss. There is a broad consensus amongst scientists that our moon formed from a collision between Earth and another large body, either right at or just after Earth's accretion. This is known as the giant impact theory. Using this theory, there should be a relationship between the age of terrestrial and lunar rocks, and in fact there is. Lunar rock samples returned from the Apollo missions have been dated up to 4.55 billion, using similar techniques as the Acasta Gneiss and Jack Hills zircons. With these three pieces of evidence, we're getting closer to understanding Earth's age, because we know Earth must be older than the rocks and materials it produced, and older than the moon. To continue constraining Earth's age, we also need material that is older than the Earth. In the 1960s, Claire Patterson began using radiometric dating on meteorites. His analysis of lead isotopes yielded the oldest age of a meteorite at around 4.55 billion years. Since then, geoscientists have continued to research the Earth's age, and today most agree Earth is around 4.56 billion years old. So when it comes to finding evidence to support the young Earth model, I think our friend from the beginning of the video put it best.
The real issue are the rocks.
Okay. Let's go back. Now, one of the great things about zircons is that we have two decay schemes. So with potassium argon, we really didn't know whether the age was meaningful or not, because we couldn't decide whether the sample had lost argon or gained potassium since it formed, since the time of interest. But with uranium lead, we've got two decay schemes. One of them is uranium-235 decaying to lead-207, and the other is uranium-238 decaying to lead-206. So if we have a good age, those two ages will agree. So here we see the Concordia curve, and what that Concordia means is this is the locus of points where the ages for these two decay schemes are the same, right? So if you analyze a zircon for both uranium-238, 206, and 235, 207, and it plots on this line, then you know you're pretty confident you've got a good age, right? Like that point. But if it falls off of this curve, then you have to come up with something else to explain it. And what we see here is 4 zircons, and 3 of them are not falling on the line. We call them discordant. One of them falls on the Concordia. We call that concordant. And we can explain this as a result of the sample or the zircons losing lead basically today. Okay, so we've got this check on the quality of our age from this Concordia analysis. Any questions on that? All right. And the other great thing about zircon dating is we have three main ways we can do it. So now they vary in the size of the sample. They vary in terms of the reliability of the age, and they vary in terms of the cost. Let's take them. So there's chemical abrasion, isotope dilution, thermal ionization, mass spectrometry, which is this CAID TIMS. Then there's laser ablation ICP-MS, laser ablation inductively coupled plasma mass spectrometry. That's this big red area. And there's also secondary ion mass spectrometry, which allows you to get a smaller spot size than with laser ablation. This is the size of an individual zircon, just 100 microns there. So, what we do with chemical abrasion isotope dilution thermal is we separate the zircons, and then we do some chemical abrasion and attack them with acids, and then analyze them on a mass spectrometer like the one I was sitting at 40 years ago. With the laser ablation ICP-MS and secondary ion mass spectrometry, you're aiming a spot at a zircon that hasn't been digested. So we don't have to get into the details, but the fact of the matter is you can get a good age pretty cheaply by laser ablation ICP-MS. And if you really need a tight age, then you're going to have to pay big bucks for a chemical abrasion. But these techniques are available. All right, so just an example, this is the Wichita igneous rocks in southwestern Oklahoma. This is the stratigraphy, and what we've got here, rhyolites on top of granites, on top of gabbros, and these are the ages of the granites. And the granites are 530, 530, 530, 530, maybe 531, and the gabbros 532, 532. It's a couple million years older. These rhyolites are out of the map area, so we won't worry about them. So you go, that's kind of interesting. The lower parts are slightly older than the upper parts, but they're all about the same age. And stuff like that really helps to resolve scientific controversies, to be able to have those age constraints that tightly defined. So here's an example of an ore deposit from Geology 2013. So we're looking at a 5 centimeter thing, basically a little slab in your hand. And from it, you can see there's the wall rock in green. There's an early porphyry igneous rock. There's an early intermineral porphyry and a late intermineral porphyry, and this has been all affected by potassic and chloride sericite alteration, very common in these ore deposits. And then this down here is a late mineral. So what they did is they went after the zircons in them and characterized them by their different zircon morphologies to try and work out the ages of it. And then some of these were dated by other techniques, including rhenium, osmium, molybdenite, which we haven't talked about yet, and the others by argon. So you can come up with a very detailed and well-constrained chronology by using these tools well. So here we've got one where this is the Polaris deposit up here in the Canadian Arctic. And here's the map body, 250 meters, very close to the sea. And this is a cross section of what the ore body looks like. And we know that the host rock are mid-Ordovician carbonate rocks, limestones, that we can constrain to have been deposited between 470 and 440 million years. So the question is, what's the age of the ore deposit? And what you're seeing here is the data for sphalerite. Sphalerite's a zinc sulfide we're seeing here. And the other one is for pyrite. Let's see, where's our pyrite? I thought we had some pyrite. No, we don't have any. So it's sphalerite, and then they leach it and see what's in there. So you can see it's incredibly low abundances of rubidium and strontium in the sphalerite. Not too surprising because, you know, Goldschmidt's rules would say there shouldn't be any, but there's always a little bit. And then these are the analytical details. There's the 87 rubidium 86 ratio that we need for the x-axis. And there's the 87-86 ratio that we need for the y-axis. And see if we can get an age for this deposit. And what we see is the sphalerites all line up on this line, which is 366 plus or minus 15. And that is considerably younger than the Ordovician carbonates. So we can see that there was 100 million years between when the carbonate was deposited and when the ore mineralization occurred. Very useful information. Now, one of the interesting tools that's come out in the last few decades is rhenium-osmium dating and molybdenite. And this is an example of serendipity, which was as the laboratory rats started understanding how to do osmium isotopes, they started looking around for minerals that had favorable ratios of rhenium, to osmium. And they found out just by trial and error that molybdenite, just MOS2, contains a very significant amount of rhenium, but very little osmium. So here's the rhenium contents, nanograms per gram. So micrograms per grams would be parts per million. So just move a period there. So this has got, that's 8 parts per million, 12 parts per million, 28 parts per million. And we use this decay scheme, and we get this very nice isochron, MSWD of 0.37, and an age of 133 million years for the formation of the molybdenite, which if we can relate that to the formation of the ore body that we're interested in, gives us another way to determine the age of mineralization. Very useful. Now, another thing to keep aware of is what these ages mean. And what these ages are, the radiometric ages date when the temperature decreased sufficiently that diffusion slowed down drastically. So what happens is in a hot system, the parent and daughter will diffuse in and out of the crystal so that, the radiometric clock really isn't set. You've got to close the mineral to re-equilibration with the surrounding minerals. And here, this is a good example of kinetics. And so this closure temperature is the temperature of the rock when the radiometric clock starts. And this is very useful because mineralization happens at different temperatures. So for example, here's the closure temperature. We haven't really talked much about the temperature of mineralizing fluids, but what you can see is, okay, let's consider a mineralization episode that happened at 400 to 300 degrees. We figured that out. We would say, oh, well, what we need to do is understand when that formed was argon-argon dating of muscovite or biotite, not uranium-lead dating of zircon, because it wasn't affected, it wasn't reset during this event, right? So understanding these closure temperatures is critical for interpreting radiometric ages. Any questions on that point? All right. So only 3 of the major ore deposit groups are really well adapted to radiometric age determinations. Certainly magmatic deposits are. They're typically form at 800 to 1200 degrees. Hydrothermal deposits are. These typically form at 300 to 600 degrees. Sedimentary deposits, they can be problematic. We did just see an example of one with the Polaris deposit, so it is possible to do some useful work on dating things using radiometric things. Placer deposits, no, these are just lying on the ground. They don't tell you anything. Laterite deposits, we don't have anything that can date them. Metamorphic deposits, they get up high enough, and that's something that we could. And finally, brine deposits, these are generally not very suitable for radiometric dating, but people are always trying to find applications for these kinds of systems. So sometimes it's easier to date the alteration associated with mineralization than the mineralization itself. And one of the stories that we'll tell over and over again is how when you're always going to have altered rocks around any ore deposit. It's because of the nature of the fluids and the heat and all of these things that make the ore deposit that affects the surrounding rocks. So, if you can date the age of the alteration, then you're basically dating the age of the mineralization. So that's something that can be done. And we'll talk more about that, alteration halos around ore deposits in this course. So these are just some of the chemical changes, and that's going to affect the isotopic systems. Matt's already shown you an example of how the stable isotopes are disturbed by these alteration halos. And that also gives us, a way to leverage the redistribution of radioactive elements and maybe get a handle on determining the age of the event. All right, so let's just finish up with looking at the sources of mineralizing fluids, not looking at the age of the deposit or the rocks, but let's look at where the mineralizing fluids are coming from. So we can use radiogenic daughter products to constrain magma sources. So we can look at three, big examples of magma sources: old continental crust, like remelting a craton. Old continental crust has high rubidium strontium, low samarium neodymium, and low lutetium hafnium. So the isotopic compositions of strontium, neodymium, and hafnium will evolve to reflect that and the magmas that come from them. Then we have the enriched mantle, which has a moderate rubidium strontium, a moderate samarium neodymium, and a moderate lutetium hafnium. And then we have depleted mantle, which has low rubidium strontium, high samarium neodymium, and high lutetium hafnium. And these differences over time will evolve to different strontium, neodymium, hafnium, and lead isotopic ratios. And these differences are preserved in igneous rocks and can be measured to high precision. There's Professor Manton analyzing some isotopes on a newer machine. So we can look at the lead isotopic system. So let's go back and just consider, here we've got a target. Let's say that's an ore deposit. And then this ore deposit is in a terrain that's placed in sort of background. And then there's a sample from somewhere in the region. And it would seem that the closer we are to the target, the more the isotopic composition would shift towards it, right? This is a scale. So at the target, the signature is 100%, and in the background, it's 0%. So we can calculate that. So here we're looking at the ore deposit. Here, we sort of reversed it. we're looking at two ratios of lead 208 to lead 206 versus lead 207 to lead 206. So no radioactive parent there at all. It's just the radioactive daughter. So you can see that the target has a very distinct lead isotopic composition, both in 207, 206, and 208, 206, than the background, say the surrounding crustal rocks. But oftentimes there's soil covering both things, and so you're not sure, where is it? And if you sample the soil, then the closer you get to the target, presumably it has more of the isotopic composition of the target. And as you get farther away, it's more like the background. So this is an exploration, a tool that you can use for exploration. Very useful. So we can also get information about magma sources inferred from isotopes. And these are very useful for magmatic deposits and hydrothermal deposits, and also useful for understanding the sources of brines. So here's an example. This is the Mesozoic batholith of Western North America, the Coast Range Plutonic Complex in BC and into Washington, the Idaho batholith, and the Sierra Nevada and the Peninsula Ranges in California and Baja California. And of course, this is the most famous example is Yosemite Valley in California, where you get these beautiful, spectacular cross-section through the batholith. What we can see in these igneous rocks is they have different strontium isotopes, initial isotopes. So here we got 704, 705, 706, 707, 708. So this high 87-86 ratio, and these are initial ratios, in the east reflects the magma source of the old continental crust with high rubidium strontium. It's old and had a high rubidium strontium. That's how this high 87-86 evolved. And this low 87-86 in the west represents a magma source dominated by young oceanic crust with low 87-86. So this was worked out in 1977 or 73. I can't tell which one. But now people working in this part of the world talk about the 706 line as basically approximating the boundary between the old rocks of the remobilized craton to the east from the accreted juvenile rocks to the west. So it goes from 4,500 million years ago to 2,500 million years ago. So this is the Hadean and the Archean. And then these are individual zircons from rocks of different ages. And you can see that as things approach the depleted mantle, we infer that there's a greater mantle input. And as things go to lower ratios, we infer that it's more partial melting of old crust that's involved. So we can extract information about the sources of the igneous rocks, and many ore deposits are also related to those sources. So that's of interest as well. It makes sense that you would, because as I said, each of the half of our lectures is basically an entire course. So it makes sense. This one's kind of neat. This is information about the Precambrian crust beneath buried sediments of North Texas, Oklahoma, and New Mexico. So what we're doing here, we're not dating rocks. We are actually determining model ages for basically the way we do that. It's complicated, but what we do is we basically extrapolate back to the depleted mantle curve, and that tells us when the continental crust fractionated from that. It's a model age. So what we can see here in the basement of Texas and New Mexico is that the crust is is pretty much the same age. It's getting older towards the north, 1.87 billion years, 1.6, 1.7, 1.7. And then it's getting younger towards the south, 1.5, 1.4, 1.3. So that is, in this case, it's got nothing to do with mineralization. The study was not designed to find mineral deposit. It was simply mapping out the crust of different ages in this part of the world. So this is when I first started seeing these lead isotope plots, I was confused. So don't feel bad if it doesn't make any sense to you, because it took a long time for me to understand it. So basically, we're looking at the evolution of lead isotopes in the Earth from the beginning, when the Earth accreted, that's primordial lead, until looks like 2.7 billion years ago. So the lead isotopic composition of the bulk Earth would have increased because uranium-235 is decaying to lead, and uranium-238 is decaying to lead-206. So with time, the Earth's mantle is going to evolve like this. And then if you extract some sulfides from it at 2.7 billion years, it's going to take on that isotopic composition of the mantle at that time. Okay, so the galena, this is all galena. Galena will not take in any uranium. So when the galena forms, the lead isotopic composition of that galena is frozen. So as time continues, to here we are today, the lead isotopic composition of today is the 207, 204 ratio looks like 15.7, and 206, 204 is 18.8 or something. That's what the isotopic composition of galena would be if we took it out today. And we can see just from analyzing the isotopes, a composition of, say, something like Kidd Creek up in Canada, that it would fall around there because it formed 2.7 billion years ago. So that's really kind of useful as well. And then we can use some of these ideas to help us find hidden ore deposits. So this is a VMS in Ontario that Matt gave me. So this is the VMS would be, this is now we're looking at lead 208, 204 versus 206, 204. So this composition was set when the ore deposit formed back in the Archean. And then Matt and his team go out and collect bark and moss. I'm surprised you don't have maple syrup on here, Matt. I'm not sure what's going on. Maybe poutine should be on there too. I guess that wouldn't be so useful, but maple syrup could. And then these are also, Matt, yeah. And then these are all till deposits and some of the till silicates. So, I think what you can do is when your team, gets these values from plants and things, you're going, oh, then we must be getting close to the VMS. Do you want to comment any more on that?
Yeah, it's basically a vector from background. So the till represents the glacial sediments that have collected rocks or collected material from a wide area. And then as you get closer and closer to the deposit, the lead isotopes become more deposit-like in the till. And then the plant samples are collected more locally. And so the humus that's further away has a more radiogenic or higher values, and the bark close to the deposit has least radiogenic or the lightest or the most close to the VMS.
Mm-hmm. So that's kind of cool. Everything is close. How close was the humus, moss, and bark to the VMS when you collected it?
I wasn't actually involved. I have to confess I wasn't involved. It was this lab. So I would have to go back to the PINS paper. Yeah.
That's fine.
Yeah.
Just curious. Won't be on the test.